we are going to the next and last talk of this paper session. This work is done by many people. I'm going to read the contributors. There is Eduardo Miranda, Richie Yeung, Anna Pearson, Konstantinos Meichanetzidis, and Bob Coecke. And I think it's Bob and Richie that will present. Am I correct? And they are going to talk about a quantum natural language processing approach to musical intelligence. So Bob and Richie, the stage is yours.
So I'm going to share my screen. Oh, something's complaining now. Share, there we go. There we go. Okay, so indeed, like was said, this is like collaboration of a number of people in Cambridge Quantum, where we also count Eduardo because he's some sort of permanent sabbatical visitor now. And the talk is a QNLP, Quantum Natural Language Processing Approach to Musical Intelligence. What you see here are two of our logos, our in-house logos. One is referring to compositional intelligence. That's some sort of AI paradigm which we push forward, where the concept of compositionality replaces the usual concept of reasoning. And the second one is our logo for Lambec, which is a piece of software which is key in what we are going to talk about and which is freely available, open source and all that. So whatever we are talking about here, you can do yourself, like by means of that tool. So basically, this is our team in Oxford of Cambridge Quantum. Cambridge Quantum, we're now soon heading to 350 people in total, but this is like the Oxford team. And these are the people who did this work, which we are now talking about. So what is our prehistory? Because the prehistory to this talk goes already a long way back. So the prehistory is that around 2008 at Oxford University, there were 3 people. So one person knew, that's Marnusha Zadeh, she knew categorical grammar. So what is categorical grammar? I'll explain this because it's really important for this talk. So this is the idea for those people who don't know, that you've got some sort of algebraic system. You could call this a type system, although it's much more like of the sort of 50-year ago nature of algebraic logic. So you got some primitive types like a noun type, a sentence type, and then you got some composite types like for transitive verbs. And then by doing some algebra, you can actually verify whether a sentence is well formed. Like the little calculation I show here is that you got a noun, say a subject on the left, a transitive verb in the middle, which includes like these 3 simples and these -1s, an object at the right, and then the calculation of the system will teach you that you end up with a sentence. Now, one of the nice things of these calculations, which is due to Lambec, actually this entire field is pretty much due to Lambec, going back to the 1950s in the previous century. So, but at the end of the previous century, Lambec sort of realized that a lot of these calculations could be represented by nice little diagrams like here. So it's a bit like in physics. You see an n, you see a -1, and they kind of annihilate each other, like in field theory. And here you see n-1 and then they annihilate each other, the sentence type goes through. So the little calculation which you see here can actually be represented diagrammatically, and that's kind of important. Okay, so this is a story about grammar algebra. At the same time, also in Oxford was Steve Clark, who just had become faculty, and he started to talk about vector space semantics of meaning. Now, today, this is not something you have to explain to anybody anymore because everybody knows this. This is just everywhere around us in AI. But at the time, it wasn't really not that prominent yet. So Steve was one of the specialists of the field. And yeah, he was working on that. And then there was me, who knew nothing about language whatsoever. He couldn't even write his own name and stuff like that. But I was developing categorical quantum mechanics at the time. So what is categorical quantum mechanics? It's sort of a diagrammatic reformulation of quantum mechanics, which you now find in this book, also known as the Dodo book. So these are all of quantum mechanics diagrammatically reformulated. And for the purposes of this talk, you can think of this is a book of quantum natural language processing. It's equally valid for that purpose. Anyway, so we had these 2 people who knew grammar, and me, the one who didn't know, or language, and me, the one who didn't know anything. And the question they were asking, and this was not them, this was an open question in the world, was how can we combine grammar and meaning? Meaning not in the true theoretic sense, but meaning in the sort of vector space sense. So there was no real solution to that problem how to combine the two. But I mean, despite knowing nothing about grammar, like in 2004, I was giving a talk in McGill, Montreal, at the very beginning of this sort of idea of categorical quantum mechanics. And so I presented quantum teleportation, and in the audience was Jim Lambeck. He said, "Bob, this is grammar." So he saw quantum teleportation, he screamed, "Bob, this is grammar." I said, "Oh." So of course I remember this when Steve Mernuj asked this question. I remember this, and I said, "Well, we've got the solution. Categorical quantum mechanics unifies grammar and meaning. And it actually does it in a very canonical way, in some sort of minimal way. So there is really no better solution." So we wrote this paper. We basically took categorical quantum mechanics and declared it to be a compositional distributional model of meaning. So basically a diagram like this, on top you get meanings, and the bottom is really the grammatical structure, which I showed earlier as a diagram. And so this is how the two interact. And this is literally an algorithm on how meanings of words compose to give meanings of sentences. But I can also read this as some sort of quantum teleportation diagram. It's exactly the same picture. So meanwhile, recently we've been implementing this stuff on quantum computers. I'm not going to give too much details to it. The first implementation we did was 2020 and disappeared in this paper. Now we're doing things much larger scale with a corpora of sentence of multiple hundreds and stuff like that. And basically the software which we use to do all these implementations is called Lambeck, after, you can guess who, the person who screamed in 2004, "This is grammar." So basically we released quantum natural language processing to the world. And so now there's I mean, people maybe can give links. We've got a Discord community, there's an online tool, you can get an archive and so on. But that's not what we are talking. So basically what this does is it changes language in a quantum circuit. But that's not what we're talking about today. Today we talk about musical discocat diagrams, because these diagrams, we call them discocat diagram, distributional, compositional, categorical meaning. And so this is the first step. And then Richie going to take over after this. So you replace words by musical snippets. You replace verbs by sequencing operation, like how you put things together, like an old-fashioned sequencer. I used to have like a really sequencer when I was young. And then the cups are sort of the mapping of the snippets it's the wiring of the things in the sequencer. So you get a very natural musical setup, and this also works for other grammatical type. So I'm now gonna get out of this so that Richie can take over. Stop share.
Can you hear me?
Yeah.
Yep. Can you see me? Can you see the screen? Can you see my mouse? Can you see everything?
Yes.
Okay, good. All right, so thanks, Bob. So I'm gonna pick up from here and yeah, talk about our paper. So Bob has kind of described a bit of the motivation already. Let me say it again. So the reason we're doing this project, the motivation of it is that music is a non-verbal language. Languages have grammar. So why don't we apply grammar where natural language processing approaches to music? So before I get into this musical discocat, this musical grammar, let me first talk about regular language grammar and take English grammar. So here we have the sentence, Bob plays guitar. Here Bob and guitar are nouns, so they get assigned the type N. Plays gets assigned this strange type because it's a word that takes in a noun on the right, a noun on the left to return a sentence. And this is what is known as the pre-group grammar formalism, and this is something we use in the discocat model. Here you see two versions of this. The first line here is an algebraic version of what's going on. These NRs and NLs act as right and left inverses for the grammar. When you combine the words, the types of the words together, they cancel out, and then you eventually get something of a sentence type. If you get a sentence type, then you know your sentence is well formed as a sentence. Here's the equivalent version, but written in diagram form. So you start with these types at the beginning, and when you read them from top down, you get the same cancellations as before, but in diagram form. And for the rest of this talk, we're going to use this diagram notation to indicate our pre-group parse trees. Now, using the preview grammar, we're going to use what is known as the DiscoCat model to take our language diagrams and convert them into quantum circuits. And how does this work? Well, here's another sentence. Pearson prepares tasty dinner. In the DiscoCat formalism, which is very similar to, analogous to the categorical quantum mechanics formalism, you're allowed to rearrange the words, bend the boxes around without changing the meaning of the output circuit when you convert it to the quantum circuit. So that's exactly what we're going to do here. We're going to take the Pearson box and the dinner box, and we're going to rotate them around such that the connectivities are still the same. But when we map them to quantum circuits, and the way we do this is using a functorial transformation, which in simple terms just means you take each box and you open them up into a subcircuit, and overall you get a larger circuit. This is what you're going to get here. So on the right-hand side, you're going to get a circuit that very much resembles this diagram you have on the left. And you have this open wire here, and when you measure this open wire, you're going to get an outcome, and this is going to be the basis of your model. Rewriting these boxes, these wires is very important because these cups actually correspond to Bell measurements, which is useful in quantum teleportation. However, they're actually quite expensive because you need to apply not only a C0, a Hadamard gate, and then two post. Not only does you do that, you actually have to do two post selections at the end. And that is something that is very computationally costly to perform on a quantum computer. Let's talk about the task that we picked for our paper. In the paper, we decided to train a model to distinguish between two styles of music, rhythmic and melodic. It's a bit hard for me to explain what rhythmic and melodic is without using these words, but I think we're going to play some pieces after this session, so you can listen to the music we generate of these two styles and judge for yourself. And the way we train our model is using something known as machine learning. So the way machine learning works, very briefly, to those who don't know, is you first define a loss function to characterize how well your model is performing on the data. You take some generator examples. In our case, we had about 100 sentences, and we took a portion of them to train on. So the model looks at these sentences and it has to adjust the parameters until the loss function is low. Once we have a good model, then we're going to evaluate this model by running on the test examples. This is just a quick overview of machine learning, but yeah, this is what we used. Let me talk about the musical grammar that we used to generate these sentences. So to generate the 100 sentences, we first defined our own musical grammar. And the way the musical grammar works is that we had some musical words, and these musical words are composed of single notes or a sequence of notes. And these words fall into 4 categories. There's ground words, there's primary words, secondary words, and tertiary words. And these words are the elements, or the words of a language. And underneath here, you see 3 boxes, and that describes how we're going to combine these words to using grammar to form an overall musical sentence. So take this first rule, for example. Motif rule tells you that 4 primary elements combine to make a motif, and motif followed by a secondary element gives you a musical sentence. Third rule tells you that if you had 2 sub-sentences, you can have a tertiary element followed by 2 sub-sentences to form another sentence. Here's an example of some of the musical snippets we chose to be the words of our language. Here is the snippet for ground element 1, and then this is snippet for ground element 2. Yep, so here we wrote a parser to parse our musical grammar. So this is a context-free parser because the language we define is in fact context-free. So here we have a musical sentence that features in our corpus. We run it through the context-free parser, and voila, it outputs a grammatical parse tree for that sentence. Conveniently, this diagram shows all three of the rules. So you can see it in action here. These words start with P, so they are primary elements, and they form to combine to form a motif. You can see the rest of the rules here. Right, so before we can use the DiscoCat model to train on our musical, we must find a way to convert our context-free sentences diagrams into a pre-group diagram. And this is exactly what we did. In the general case, this is a hard conversion, but in our specific case, there is a very neat functorial conversion to convert such diagrams by taking each of the grammar rules and expand them into cups and wires. I'm not going to go through the rules specifically because it takes too much time, but essentially the choices are made such that the same kind of connectivity is preserved and the algebra is preserved. Here's some code that performs this. So we implemented some code to perform the functorial transformation. On the left-hand side, you have the context-free parse tree we had on the left. We apply this functor, we take each of the boxes and we expand them into cups and wires. And now you have something on the right that very much resembles what we had originally, except it only has cups and wires and no grammatical rules in the middle. So it is can be applied. You can apply DiscoCat to it. And now, as I described before, in DiscoCat, you're allowed to move the boxes around without changing the connectivity, and you can still get a different circuit that performs the same kind of calculations. So we wrote a routine that bends the boxes around such that the connectivity is still the same, but then the outcome gives you a much more efficient circuit. Now we can take this diagram and convert it to a quantum circuit using Lambec, which is the in-house tool we've developed for QNLP, which is open source and freely available to everyone. And you can see again on the left-hand side, you have the diagram we just arrived at, but with the labels removed. By applying this functor, you now get a quantum circuit, and the shape of the circuit is very similar to the original diagram, except each diagram is replaced with a sub-circuit, and the sub-circuit consists of these gates with rotations, and the rotation phases are the parameters of our model. Here's the same circuit drawn a bit bigger, thank goodness, so we can actually see the gates. So at the beginning, we start with the all zero state. We apply the Hadamard gate, we apply some rotations and control rotations to prepare the quantum state for our sentence. And then after that, we apply these black boxes, which are just measurements. These measurements are actually post-selections. So we have to measure and make sure the outcome is zero. If they're not zero, we have to discard this particular circuit and run a different circuit. So once we have collected enough circuits and they're all zero, then we can measure this open wire here. And when you measure the open wire, if it's zero, then you know it is a rhythmic piece. If you measure 1, you know it's a melodic piece. So this is the basis of our model. So far, here's a diagram that describes what the model I've described so far. You have a context-free parser, which takes in a sentence and produces a parse tree. And then you take this context-free parse tree, you run it through a functorial transformation, which turns it into a pre-group diagram. And then we run it through a pre-group optimizer, which bends the boxes around. And finally, we're going to apply a functor using Lambec, which transforms it into a quantum circuit. And this quantum circuit, when you apply the measurement on the open wire, gives you the prediction of the model. Cool. Due to resource considerations, we decided to not train the entire model on the quantum computer. Instead, we did some pre-training on a classical device using tensor network contractions. And once we've done the pre-training, then we trained on a noisy quantum simulation, where the noise of the simulation is it resembles the actual device we're going to test on. And once we've done this training, we decided to test on the actual device, which is the IBM Q Guadalupe device. It's got 16 qubits. it's got 32 quantum volume and 2,400 clocks, which is we chose this machine because it is relatively fast and a high quality machine, and it can actually fit all the circuits that we wanted to run. So we did some training and we got some decent results. The training curve and the dev curve were pretty good, and the test results we actually got we converged to 76%, which is pretty good considering the fact that there is a lot of noise on the quantum machine, and also this is a rather subjective data set. It's often quite subjective whether a piece is rhythmic and melodic. So now that we have a decent musical classifier, we then we had a generation process. We decided to generate quantum music. So using this train classifier, we first sampled musical pieces using our context-free grammar. And once we sampled a piece, we passed it through the classifier that we trained and to see whether it is a class that we are interested in. So we want to generate rhythmic music. We're going to generate a piece, pass through the discriminator, the classifier, to see if it's rhythmic music. And if it is, we keep it. Otherwise, we're going to discard it. And we repeat this until we have, say, like 10 songs of that class. So we did this for both classes, and we generated some quantum music. On the right here, there's a musical score, which we call Alice's Caffeine Rush. I think it is a rhythmic piece. You can tell that from the notes on the score. Okay, conclusion. So yes, we applied QNLP approaches to music. And for future work, I think as we get larger and larger quantum devices, we'll be able to train harder classifiers to generate more interesting music styles using the same approach. Another thing we might be interested to do is to generate music directly with measurements. Currently, we don't, we use this generate and test method scheme, which doesn't fully take advantage of the quantumness of the device. We would like to train a model such that at the end of the circuit, we might do the measurements, and those measurements directly tell us the musical piece. So that is something we're interested in doing in the future. So that's pretty much it from me for this talk. You can check the recordings, the scores, and the code on this GitHub link. And you can also check out Langbeck here at this link. And there's also an online generator for people who want to generate disco cat diagrams on their own without installing Python. Yeah. Thank you.
Okay. Thank you, Richie. Thank you, Bob, for this presentation. We are going to the Q&A session, and we already have a question from Leah. How does the music generation process work?
The musical generation. So the musical generation, you start off by, so we have a context-free grammar. So we take the probabilistic context-free grammar and you generate musical pieces. So but the generation process is that you take those generated sentences and you filter it using the classifier. So by doing that, if you had a very complicated distribution and you can learn it through this quantum classifier that we train using DiscoCat, then you'll be able to generate music of a certain class that is interesting, and it wouldn't be easy to generate on a classical device.
Okay, so essentially the music is generated through the natural language, right?
Yeah, so we made a generator using a classifier by using it as a filter.
Okay. Do you have any more questions on the chat? We have another question on the Q&A. Is it possible to distill and summarize a relatively general way to compose a piece embodying certain emotion based on particular musical grammar?
Yeah, I think so. Yeah, that's something we can definitely we apply the same technique to our model.
Okay, we have another question from James. Not a musical question, but wonder if a particle-based language like Japanese is more or less conducive to being modeled using Lambec than English.
That's a good question because so in Lambec there's a parser on the back end, and actually the parser we use specifically DepCCG also has support from Japanese. So specifically for Japanese, there's already existing support. Has to be integrated in Lambec in the future.
Okay, I think that summarizes the talk. If we don't have any other questions, or I think we have one on the chat. Starting from your research, would it be possible to create music out of categorical structures, exploring their symmetries and dualities?
I'm not sure what you mean exactly, but
I mean, to some extent, this is already happening here, but maybe people mean high-level categorical structures, higher order or something like that. That's what I would be imagining. And to some extent, this is also happening at the theoretical end, like we're sort of replacing this disco-cat formalism with what's called the disco-circ formalism, which lifts from sentences to text. And then that's much more amenable to higher order stuff and things where you could get a lot more power from the categorical structures, I think.
Okay, that's great. I think that now that summarizes it. We are going to, so this is the end of the first paper session of the conference.